Hey everyone, just a quick few bits about angular momentum this time. Angular momentum is one of our analogies with linear stuff. We had linear momentum, we have angular momentum as well. With linear momentum, we mainly looked at that because momentum was conserved, and it turns out the same is true for angular momentum. So while we'll have some problems at the very beginning that just ask us to calculate what the angular momentum is, once we get a little more advanced with this, we probably won't really care what the momentum is at any point in time. We'll just look at how I and omega change as a result of those. So the equation for angular momentum, that's one that's on your green sheet. It's just the rotational inertia, or the moment of inertia, times the angular velocity, or the angular, rotational velocity. Keep in mind that angular velocity is a vector quantity. We're multiplying it by a scalar quantity, and that gets us the vector quantity of angular momentum. At our level, when we do angular velocity, we just use directions as clockwise or counterclockwise, or negative or positive, respectively. And we'll do the same thing for angular momentum. Clockwise or counterclockwise, negative for clockwise, positive for counterclockwise. Now units on this are a little bit tricky. If we do units for L is what the brackets mean. We have, well, the units for rotational inertia are kilograms times meters squared. And for omega, for the angular velocity, we have those in radians per second. And you remember how radians aren't a real unit, they're just kind of a placeholder unit? Well, that means that they can sometimes just disappear from our units, and it's okay. So the units we'll see on these ones are actually going to be kilogram meters squared per second sometimes. But this format ought to look pretty familiar. This is very close to joules. Joules were kilogram meters squared per second squared. And so if we just make this change from second squared to seconds, we get a pretty convenient way to write this. And so our units for angular momentum are often going to be written as joule seconds. So kilogram meters squared per second squared times seconds gets us to kilogram meters squared per second. As I said, you won't often really care what the angular momentum is, so you probably won't see these units all that frequently either. But it's good to know anyway. So let's do a quick calculation with angular momentum. Let's say we have a cylinder with a mass of 2 kilograms and a radius of, say, 10 centimeters, and it's rotating with an angular velocity of 3 radians per second. And we want to know, we'll make that clockwise. Omega is a vector, and we want to know L, the angular momentum. Well, that's going to be I times omega, but we don't know what I is, so that's where we need to start on this problem. When we have a cylinder, let's say this is a solid cylinder, and so for a solid cylinder, we have an equation for I, the the rotational inertia. Now, the rotational inertia for a solid cylinder is given by the equation 1/2 mr squared, and then we have times omega. And so from here we know everything that we need to plug in. We've got our mass here, we've got our radius, we've got our omega. So let's go ahead and plug in and solve for L, the angular momentum. So we have 1/2 times the mass of 2.0 kilograms times the radius of 0.1 meters, 10 centimeters, 0.1 meters, and that gets squared, times omega, 3 radians per second. And so we're going to get a value then, see, 1/2 times 2 is just 1, 0.1 squared is 0.01, times 3 is 0.030, and then the units on that, remember, are joule seconds, or kilogram meters squared per second. Now again, the important part on these ones is not that we can calculate angular momentum for some object that's rotating at some moment in time, but that we can do it for, say, collisions or interactions between objects, or situations where an object changes shape. One that you'll see from time to time is where we have an impact between two things. So maybe we have like, there we go, like a stick hanging down, and we have something else make contact with it, wham! And we get some rotation as a result, rotation around where my hand is here. Well, in order to understand that, we treat this as a conservation of angular momentum problem. Now the stick was moving in a straight line, but we can still think of it as having rotational momentum, or angular momentum. So another problem you might see here is we have this rotating platform, something like this. And as it's rotating, something about the way the mass is distributed changes, or we add mass to it, something along those lines. So you might see one where we have this thing rotating, and then we drop something else on top of it. Let's do that. And we see that when we drop the other thing on top of it, it slows down. And where we drop that thing matters. So if I drop it right in the middle, very little change in velocity, and in angular velocity here. If I drop it toward the edges, we have a much bigger change. Well, what's going on there? This thing has no rotational momentum to begin with, or angular momentum, and this thing does. But together they have some total amount of angular momentum, and after this is dropped, they have to have the same total amount of angular momentum. But now this thing is going to be moving around, and so some of the angular momentum that the platform had is now transferred to our weight, and so the platform isn't going to be able to rotate as rapidly. And they have to rotate at the same rate, so we can treat them like one big object with kind of a funny mass distribution. Another one that you see is this on a little bigger scale, like maybe somebody is riding around on a merry-go-round, and as it goes around, so they're already on the merry-go-round, but as it goes around, they start to walk toward the center, and they change how the mass of the merry-go-round is distributed. Or they start at the center and walk toward the outside. So those are all problems that we can solve using conservation of angular momentum. All right, so here's our example problem situation, something I'm sure you've all experienced. I'm going to be bowling while standing on a rotating platform and crouching down. Obviously, we've all done this a few times. So I'm going to start to roll the bowling ball toward the camera here, but I'm not going to do it right in front of me like this. Instead, I'm going to bowl it. So let's see what happens when we try this. Here we go, and okay, great balance, right? So why did I start to rotate when the bowling ball wasn't rotating? It was moving in a straight line. It had angular momentum, and the total angular momentum of me and of the bowling ball has to stay constant. So let's do a problem around that idea now. All right, I've made some estimates on numbers that we can use with this problem and written this up as a problem that you might see on an AP exam. So let's read through this. Got me standing on a platform. The platform was free to rotate, we know. And I was holding a bowling ball. The bowling ball has a mass of about 7.0 kilograms. And then I rolled the bowling ball at 2 meters per second, give or take. And I was rolling it in a straight line, but remember, it wasn't a straight line away from me. It wasn't like this. It was a straight line that was off to the side here. And so I'm saying that from the path of the bowling ball to the very center of rotation, that's about a 0.5 meter distance there. 0.5 meters from the center of rotation, and then as a result, when I started rolling it this way, I started rotating this direction. So I kind of pushed myself off in this direction, pushed like this. So the platform and I started to rotate at 2.8 radians per second after that push. And now we're looking for what is my and the platform's rotational inertia for this situation. These ones, there's a lot going on, and it's sometimes pretty tough to visualize this, so I would always start with a diagram. In fact, I do two diagrams, one for the initial state and one for the final state of things. So initially, we have me and the platform at rest, and we have the bowling ball also at rest, and we have a distance here of 0.50 meters. And then in our final state, omega equals 0, and v equals 0 to begin with. And then in our final state, we have me, and I was rotating around this direction. Omega, it tells us, is, where is it? 2.8 radians per second. We have the bowling ball moving off this direction at 2.0 meters per second. We still have this distance, 0.50 meters. And we're looking for the rotational inertia for this, for the Bennett platform combo. All right, so this is a conservation of angular momentum problem. So we know that we have rotation in this problem. We have two objects. I saw that I gave this thing a push, and as a result I have this interaction. There's no interactions between me and anything else, though, that would change my rotation. So when I'm just sitting there before I pushed on the bowling ball, my rotation wasn't changing. There's no interactions on the bowling ball besides me pushing on it that's going to make it have this velocity, at least if we ignore friction and air resistance, which you know we'd like to do. So let's neglect those things. We'll say that they are negligible, at least for this very short period of time while we have that push. So we're looking at the moment right before the push, the moment right after the push. We have a closed system. We have just me and the bowling ball and the platform that I'm standing on interacting with each other. Nothing else. So in this closed system, the Bennett platform bowling ball system, we could have we could do calculations for rotational momentum, and we know that it's going to be conserved. So we write that out as the total momentum initial, angular momentum initial, equals the total final angular momentum. This is the conservation of angular momentum. So we've done the conservation of linear momentum in the past. We've done it once in the x direction, once in the y direction for two-dimensional problems. Now we can do rotational motion as well. We have two objects that we have to consider. Now on the initial side, we don't have any motion whatsoever. So the initial side of this thing is easy. There's no motion, there's no rotation. That means there's no rotational momentum either. So the total L initial is just going to be 0. Which means our total L final has to be 0 as well, because they're going to be equal to each other. This one was 0 because we had nothing moving. This one, the final state, is going to be 0 because we have some positive angular momentum for one object and some negative angular momentum for the other, but the magnitudes of those are going to be equal to each other. So some positive number and the same negative number. So let's figure out what the rotational inertia is based on that idea. So this will be the final angular momentum for me. That's a vector, plus the final angular momentum for the bowling ball. And that's a vector as well. Now, for angular momentum, no, that's just I times omega. So 0 equals I Bennett. Hey, I am. Times omega final for Bennett. And I'll just call that Bennett, but it's really me and the platform. Plus, and that's a vector here, I for the bowling ball, times omega final for the bowling ball. All right, and that's the equation we're going to work with to solve this problem. Now this equation is a little bit weird because we have this omega for the bowling ball, the angular velocity for the bowling ball. But angular velocity we usually use for things going around in a circle, and that's not what the bowling ball is doing. It's going in a straight line. But if we just look at a single instant in time, we can't tell whether it's going in a straight line or around a circle. And that's what we're looking at. We're looking at the instant right after I finish pushing that bowling ball and I start to rotate the other direction. In that instant, for all I can tell from this snapshot, this bowling ball is going to go around in a circle like this. Maybe it's traveling on a circular path around the platform. And so does it make a difference that we know it's after this not going to follow the green path? It's going to go in a straight line? Well, if we're looking at just an instant in time, No, it doesn't make any difference whatsoever. So we treat it as though it's going to go around on this circle, and then we know that if it goes around at 2.0 meters per second, and it has to go around this circle that has a radius of 0.50 meters, we can figure out how much time it takes to go around once, and that's 2 pi radians to go around once divided by a certain amount of time. Or we know the relationship between v and omega. We can do v equals omega times r, where r is the radius of this imaginary circle that, admittedly, the bowling ball isn't really traveling on. It's just the distance from the bowling ball to the center of rotation. And then the speed is going to be our 2 meters per second. So our omega then, if I rearrange this, will be equal to the speed divided by the radius. So that's 2 meters per second over 0.5 meters. And then our meters cancel. We're left with 4. And the units come out as 1 over seconds, but we know it's really radians per second. We just have, the radians kind of disappear and reappear because they aren't real units, but radians per second for that one. All right, so we've got 4 radians per second for that omega. What about I, the rotational inertia for the bowling ball? Well, we still need to treat it as though it's going around in this circle for this part. And so I is equal to, well, what kind of an object is this? Oh, that's a point mass that's going around in a circle. It's not some mass spread out over the entire circle that's rotating. It's a single mass that's going around the outside. So the rotational inertia for that's actually on your equation sheets. That's just the mass of the bowling ball times the distance squared, mr squared. So the mass was 7.0 kilograms. The radius is 0.50 meters. And we square that, so 0.5 squared is 0.25 times 7. That's going to give us 1.75 kilogram meters squared. At this point, back to this equation, we know omega for me, we know I for the bowling ball, and we know omega for the bowling ball. And so the only thing we don't know is I for me, which is a very strange statement here, but I of me, I don't know. 0 equals I Bennett times omega Bennett. That's 2.8 radians per second. And let's take a minute to think about directions here. Let's see, this one is rotating this way. That'd be in the clockwise direction. We use a negative for clockwise rotation. Plus I for the bowling ball is 1.75 kilogram meters squared. Times omega for the bowling ball is 4 radians per second. And again, let's take a minute to think about directions. The bowling ball goes around this imaginary circle, or just this one spot on the circle, but it's going in the counterclockwise direction. That's a positive 4. All right, so now we have 0 equals I Bennett times 2.8. Sorry, negative 2.8 radians per second. Plus 1.75 times 4, it'd be 7. And then that's kilogram meters squared per second, or joules second would work there as well. And then our final answer, we'll move the 7 over to the other side by subtracting it, and then divide both sides by negative 2.8, and we get I Bennett is equal to 7 divided by 2.8, which is going to be 2.5 kilogram meters squared. I misspelled my own name in there. That's pretty good. Okay. Conservation of angular momentum problems will look a lot like conservation of linear momentum problems. The only thing that's going to be different about them is that instead of m's, we have i's, and instead of v's, we have omegas, the rotational quantities for inertia and for velocity. Other than that, though, they're basically the same setup. It's a little tougher to imagine collisions with rotating objects, but we could still have that kind of thing going on here as we did here.